Hello, everybody, and welcome to episode number 67 of the Hyperthesis podcast, our second episode of the year. I'm Patrick.
I'm Pheely.
And I'm Liam.
As you can hear, Liam has now delved off into ASMR. But today we'll be talking to you about a lot of interesting topics. We've got some heated AI topics coming to you in our main topic and story. But before we get into that, does anyone have any intro topics they want to discuss?
I have one, which I haven't had very much time to research and look into, but I want to mention it because I think it's kind of neat. So there's a postdoctoral researcher named Barbara Soda, which maybe I pronounced the last name wrong because there's a little symbol above the S, but it's spelled soda. So I apologize if I pronounce it wrong, but I'm just going to go with that because I don't know what it's supposed to be. And they are postdoctoral research at Perimeter Institute in Canada, so just up the road from where I am and a place we talk about often. And her theoretical work with collaborators turned out to be developed into a preliminary experiment by a team of researchers from Chapman University in California. So I mention that because usually when you come up with a theory, you're dead by the time the experiment's implemented, or you're really old. So it takes a lifetime for a lot of theory to move into experimental stages. Not always, but often. But turns out the stuff she did during her PhD thesis is already being created in experiment because it has really, really large, a really large range of applications. So her work was published in August 2023 in Physical Review Letters in a paper titled Super Interferomic Range Resolution with some other co-authors. And it could lead to a kind of super radar that would have many practical applications. So we've talked about radar before, multiple times, I think, but radar...
Well, I think in terms of the experiment, it really depends on what you work on or your field, right? I think in condensed matter or like material science is much easier to perform experiments or, if you postulate that there are material that looks like this or have this structure, it should have this property, it's not too difficult to create an experiment to manufacture or create that material, or sometimes it's really difficult, so it really depends. And secondly, when you talk about super radar, I think everybody is thinking about the same thing, right? Like it's the practical use, probably military.
Yes, military, and also I think like you can use it to look at things inside the Earth as well, a whole bunch of them.
If you want to learn more about that, go listen to our episode with Zoe Vestrum, who uses radar to look inside the Earth.
Yes, so we've talked about radar a few times before, but radar signals, they're actually, a radar wave is a light wave, just like the visible light we see or the microwaves that are produced in a microwave oven. The difference is that radar waves have very long wavelengths compared to the other forms of light. So they can be anywhere from like 10 meters long to 100,000 kilometers long. Visible light is in the range of about 400 to 700 nanometers, so that's way, way smaller than radar waves. And radar waves, like we mentioned, they have tons of applications. Radar guns that police officers use. I don't know if those we've had this exact conversation before. I don't even know if those use radar, right? Okay, because I was just wondering if they're improperly named or something, but they do use radar. But because radar waves are so long wavelength, they're not really good at interacting with smaller things. So when you image the inside of a human body, you use X-rays, which are really high frequency, small wavelength waves with high energy. So they can really resolve things inside the human body, although they produce more energy and can be more harmful. So ideally, you might say, why don't we use longer wavelengths, which are less energetic and won't hurt you as much? But because they're so long, they can't resolve the fine structure of smaller things. So Soda's work with her collaborators was to make radar more broadly applicable and better manage this trade-off between wavelength size and resolution size. So she helped develop this method of improving it, which involved these so-called super oscillations. So normally waves only oscillate kind of as fast as their highest frequency component. So if you think of like a perfect sine wave, it has a single frequency or a single wavelength, but you can add together different sine waves. You can take superpositions of them to create different types of waves with different frequencies. And the physicist Yakir Aronoff, the guy from the Aronoff-Bohm effect, who's quite a famous physicist, he found that if you take special combinations of sine waves, you can actually produce regions that oscillate faster than any of the constituent waves, which we now call them super oscillations. So I don't personally know a lot about this, but I want to read up on it and come back and talk about it another time. But these ideas by Aronoff were developed further by Sandhu Popescu, which I might have pronounced wrong, and Sir Michael Berry, funnily enough, who I mention a lot, from the University of Bristol. So people like these physicists theorized that you could use super oscillations to improve the resolution of radar before, but it wasn't really clear how you could generate these super oscillations. So that's where Soda and her colleagues came in. They provided kind of mathematical tricks for constructing and designing these super oscillations, and they did so in a way that you can kind of design and shape the super oscillations such that they're oscillating the way you want them to. You can kind of precisely design them to have specific oscillations that you want. And doing this, they were able to demonstrate that you can increase the radar range resolution by more than 100 times better than the kind of previously believed limit. So you can imagine that has a lot of applications, and it's just kind of the beginning of their limit breaking research. They'll probably break the limit more in the future, and who knows what they can do from there. But I don't know. This article, I found this paper and I found this article talking about it, and it started off talking about how they've developed experiments which are starting to match this theory, but then they never mentioned the experiments again. So I unfortunately will have to get back to you on that. So in the future, I want to read up on these super oscillations and try and find a paper for this experiment, how did they create them? How do they plan to go about this?
It'd be very interesting to see where this research goes in the future. Just like you said, there are many uses for radar, including looking at the Earth. And one of the main Earth observation technologies, that's one of the oldest, is radar, where we have radar operating satellites that scan the Earth. And I mean, who knows what the military has? It could be more advanced, but we have radar resolutions of under a meter now. So you can tell the structure of something, or if there's an object, like say a car or a person or even a little box, just based on radar scanning from space. So using something like this, I mean, we might get similar results to LiDAR, which you can get, I mean, millimeter or even micrometer resolution from LiDAR. I'd be curious to see like how powerful you can get this with this kind of improved range resolution. And also in terms of astronomy, if you could use it in that instance as well.
Yeah, because they use that. I mean, this is a completely different ballpark, but that orange black hole image, the first image of a black hole they took was with radar waves. It was a radar telescope, well, a bunch of them. And I guess if they did 100 times better than the current limit, I guess you said the current limit might be around a meter. Then
Yeah,
well,
under a meter, it could be. Let's say a meter, sure.
yeah, somewhere a meter plus or minus some amount. If you do 100 times better, then that's like 10 millimeters, maybe. Am I doing that right in my head? I don't know. Early in the morning right now.
It'd be a centimeter. Yeah.
Yeah, centimeter,
100
right?
times better.
10 millimeters a centimeter, yes. So that's already pretty good for some preliminary work that's only been around for not that long, like a year or two. They've probably been developing it for longer, but the publication came out this or 2023, so that's fast work. Impressive.
Yes, very much so.
Well, I wonder for the super oscillation, like, can we just create like higher radio wave just by itself, right? Or what? Why do you need to combine bunch of longer wavelengths to have like a not even probably more imperfect radio wave or like radar? That's kind of strange to me. There must be a reason that the radar that in high frequency is really hard to generate, but I'm not sure because I think it interesting idea, right? That instead of imagine a waveform of high oscillation, you want to go up and down a lot, right, quickly, and basically, I think super oscillation is combining multiple waveforms to actually create that shape that looks like it oscillates really fast. And well, mathematically, I think is more rigorous. But I wonder, like, well, instead of creating multiple long wavelengths, is it that difficult to generate a short wavelength radar?
Yeah, I guess I don't really know. My question is that they're using radar to create shorter wavelength radar, but why don't you just use a smaller wavelength part of the spectrum, right? So whatever comes before radar waves, the radio, maybe
Micro.
Okay. Radio after?
Radio is radar.
Oh, right. Sometimes it's like a subdivision. Yeah. So radio waves are also an example of applications of radar waves. You listen to the radio. But my question is, why don't you just use microwaves or something instead of? What's the difference between a microwave and a low or a low wavelength X-ray? That's my question. But there's probably way more to it than I'm getting into. Like I didn't fully read the paper. It might be like a distancing. It might be that you combine the radar waves and some distance away from the source they're created, they interfere such that their wavelength shrinks, so then they can resolve better or something. I have no idea. I want to read more into it though.
So just based off of what I know from radar remote sensing, and just to be clear, radar stands for radio detection and ranging, or radar. And essentially what happens is that we kind of class microwave and radio waves together. So a lot of remote sensing devices that are used to, say, construct the 3D surface of the Earth are actually microwaves, but there's issues with penetration. So any type of wave, whether it's a sound wave or a light wave, will have issues penetrating a medium the further it travels along that medium. And so something like blue light is lost at sunset, whereas we can see a red light instead because of its longer wavelength. It's able to penetrate easier, just like how you can hear your neighbor's bass as they drive by in their car, but you can't hear the highs. And so a useful application of this is when you want a very high resolution image, which you can only get with high frequency radio waves or microwaves traditionally. Instead, you can send these lower waves or lower frequency waves through, and then it seems like they'll kind of construct or destruct in such a way that the frequency is increased, and so they have a higher penetrating power, and so you can still get that signal at a higher resolution using lower waves.
I was reading it briefly. It looks like super oscillation is a good alternative to generating high frequency because they said the common high frequency usually generate from some nonlinear effect of high oscillations effect. So that might be really difficult. But usually things low frequency is much simpler. So
yes, you can avoid a lot of mathematical problems with low frequencies. I know that much. Also, they're lower energy, so lower energy is always easier.
Exactly. But with that, I think we can move on to the main topic, if no one has any final words. And for today's main topic, it's about machine learning specifically. So this is a kind of buzzword nowadays where machine learning is becoming synonymous with technology, and there are so many applications of general artificial intelligence that are being applied, whether it's in your phone or in your car or computer, kind of wherever you are. It's very hard to escape artificial intelligence now. And just as a precursor to possible future talks in artificial intelligence, I wanted to give more of a background on machine learning specifically, which is technically a subset of artificial intelligence, according to the sources that I've read. And so, uh, machine learning is kind of almost a precursor to artificial intelligence, but the idea of it hasn't been around as long because the idea of some sort of computer intelligence has been around for a while, but there are a lot of useful applications for machine learning, and it's important to understand what's exactly happening behind the scenes instead of just saying, oh, it's a computer thinking for itself, because that's not really accurate, at least at the time of recording. If you're listening to this in like 2060 and the machines have taken over, uh, well, good luck. So, the idea of machine learning is, again, everywhere. So it's in your Google searches. It's if you used Siri or Alexa or Google Assistant. You've used some form of machine learning, even something like the YouTube algorithm. So if you've watched a video on YouTube, there's some form of machine learning there. And most devices nowadays have machine learning built in. I just saw that they're releasing a new Windows keyboard to work with Windows 11, where it will have a specific AI button, which I think is called Windows Copilot.
Oh,
Yeah,
what does that do?
interesting. It's I think Microsoft's new assistant, which is I haven't looked too much into Copilot. It freaks me out too much.
They should keep Cortana and make her like absolutely great. I want you to be like Cortana, steer the ship.
Yeah. Cortana, where's the chief?
Yeah, so even Cortana, there's another example of a interestingly implemented machine learning assistant. And maybe one day Cortana will fire on some vessels. But nowadays,
Well, in the lore, she's gone rogue in Halo, so I've kind of lost track of it, but she's a bad person
To
now.
save save us all.
She went rampant to save us from ourselves. Anyway, video games aside.
yes, and killer AI aside, because if AI is listening to this episode, then we want to put it in a good light.
Pheely might have something to say about killer AI later. Maybe. I'm not sure. He could. We'll see.
Yes, a little bit of a teaser there, Liam. But for now, before we get into AI, let's discuss what machine learning is. So, to start with, artificial intelligence is kind of a broader term for different algorithms that are able to essentially learn. So, they are programmed in such a way that some sort of input data can be introduced to the algorithm, and then it can manipulate itself in such a way that it's able to learn based on either positive or negative feedback loops or both. And it's able to adjust its parameters to better handle the input data. Machine learning is similar to this, and I don't believe that there's actually a fully fledged AI, but we'll get into that in a second.
I think we should clarify the concept of intelligence too, right? Because, well, what do you mean by intelligence? And I think one of the main way you can think of intelligence is that, well, how do the system or person or thing deal with new scenarios or new information? How you handle that is because let's say the standard computers. Well, some people say, "Oh, it's very intelligent," but is it? Because it really perform commands that already coded into the computers. They do it really well, really fast, but they are predetermined patterns. It's like tools, right? If you have a jackhammer, is programmed or designed to do the jackhammering, to break some stuff, but doesn't mean it's intelligent, right? So I think in this case where, like Patrick say, you make it learn so it can adapt to new scenarios or new information that comes up.
Okay, but if a person goes on the Jeopardy game show and they have like millions of facts memorized, but they can't adapt, then would you still call them intelligent or not? I would, but it's a different type of intelligence, maybe.
I mean, that's an interesting point, but the person is also capable of feelings too. Like, and even for example, they're able to describe things in more detail, whereas the machine might have just facts readily available, but they might not have memories associated with those facts and where they learned those facts, why they know those facts, kind of thing. And I mean, there is just rote memorization, but there's an added level to it when it comes to actual intelligence.
Well, yeah, because you have a billion pieces of information. If you're a computer, you have to devise a search algorithm to even find information in Jeopardy, which is a competitive scene, right? Like you have to be quick to get to the information. I think that is a skill too, which I like the computers. We have search algorithm that we coded in to efficiently find information we want, right? Like how search engine works. And like, but humans, we kind of have to do that. Well, we had to learn how to do that. And I'm sure search engine these days have some kind of machine learning to learn how to efficiently search the data.
But your brain is just a very fancy computer, isn't it? I don't. It's weird. Brains are funny because somehow they weigh like a couple pounds or something, and they're the most complicated objects we know of ever. So this getting more philosophical maybe than it is technical, but
So, in that case of whether machines are simulating the brain or the brains are just glorified computers that are made of fat and meat and all that, let's talk about what exactly these algorithms do. And to start, we have discussed intelligence just briefly, but artificial intelligence is the idea that some sort of computer algorithm is able to change itself and teach itself in a way similar to our brain. And so it's this feedback network that utilizes training data to self learn, but it's also able to self adjust and self replicate, kind of. So I don't think that we have a true AI technology because there's nothing that's actually simulating intelligence in the way, in the complex way that we just discussed, in which we're able to think and feel and interpret the environment. The AI that we have now, such as the large language models, think like ChatGPT or Bard or um, all these different AI models, they aren't true AI because they don't really think for themselves. They use quite a complex algorithm, but instead they're really just algorithms that know how to piece words together. And they've taken things a step further. They can interpret and summarize and provide feedback, but they're still just really clever algorithms that know how to put words together, but that's kind of the maximum level they have. They aren't truly thinking for themselves from what we can tell so far. There's some controversy around that, but generally they don't think for themselves. They just do what they're programmed to do.
Well, the language models, right? They study language. Basically, they learn how human language works and how to weave them together in a clear way. And a lot of people, I mean, humans learn to do that too. But each person has their own way of understanding words, and I think there are a lot of more philosophy that you can discuss on how actually language shape our understanding of the world. And I think this AI or this machine learning, that way that people do for language model, really, I think it will show how actual language, how information manifests through language. I think it's a very interesting thing. People are more interested usually in the practical aspect of this, right? Oh, when can we use it? Where can we use it? Can we use it to edit our papers or essays and stuff, and maybe write some summary of a lot of topics? But yeah, like Patrick said, it's not really. Oh, we don't know. Well, we are pretty sure that they don't really understand it. They just weave things together. But then it has to come to the definition of understanding, right? If they can group up all the relevant um, information to what's it called to the certain field, and everything seems to be at a correct relationship between one another. Well, does it mean you understand it, right? So if you group the word force with things that like Newton's law and all these rules or things that have to do with forces, what does it mean you understand it? Or does understanding mean you can apply it? So I think it's still a long-standing question in what do you call it, pedagogy and how and epistemology. So I don't know. There's like episteme and techne. There's some Greek word on like the type of knowledge. Let's see what happens.
Yeah, that's uh, yeah. It's fair to say I think that AI is not truly intelligent as described by those different fields of thought, but taking a step back from AI and reducing it to just a subset of algorithms that are known as machine learning. So that's more so what the algorithms that we're looking at today deal with. And it's actually a term that's not as old as artificial intelligence. As I mentioned earlier, that's been around for a little while. In fact, we mentioned it last episode with Ada Lovelace, where she discussed the idea of artificial intelligence and how a computer could simulate the brain. But the idea and the term machine learning has only been around since about 1959, and it was coined by Arthur Samuel, who worked for IBM, of course, one of the leading companies in that day for computers. And at its heart, machine learning is just a computer algorithm or a set of computer algorithms that uses reinforcement to recognize patterns through statistical analysis. So it's more so than anything just a pattern recognition algorithm that's able to adjust itself based on some analysis of data. So this allows the machine to quote unquote learn based on positive and negative feedback, and it will produce inferences about data that is provided to it. Now, machine learning algorithms tend to be specifically trained for specific types of data. And we'll get into an example. But as an example of how they work in their most basic sense, if you were brand new to the world, you just popped into the world as you are now, you knew nothing, and you were placed in your kitchen. And there was you could read English, let's say, and there was a stove that was on in front of you. So you see the burner glowing red, or there's fire on it, depending what type of stove you have, whether it's gas or electric. And you go and place your hand on that burner. Now your hand's going to get hot quite quickly, and you're going to pull away because it's painful. And now, you being brand new to the world, but a fully grown adult, your brain has now learned that, oh, that gets hot when it's red. And so this is a very simple feedback system of, okay, I touched it, it got very hot and painful, and it looks red. So I will say that, okay, when it's hot, it will hurt me, don't touch it. And so this was interpreted by your brain as a feedback system, and it really only takes once to learn something like this. I don't know how many people who are listening that were children and tried to do this at least once, but again, it's only once. Now, machine learning algorithms behave in much the same way, but much like our brain, it's not just necessarily one feedback loop or one single system, but it can be a whole series or cascade of systems that are being involved in this learning process. So around the 1960s, the idea of machine learning started to become more popular, and we actually started using it in computers. Now, back then, computers were the size of a room, and the way in which code was entered into these computers were on punch cards or punch tape. So these were series of tapes or cards with actual holes in them, and that was used to code the computer based on conductivity. And one of the first experimental machine learning computers was called Cybertron. For those that are a fan of Transformers, you may have heard of it. But it was developed by Raytheon to analyze sonar signals, electrocardiograms, and speech patterns, and it used rudimentary reinforcement learning. Now, I won't delve too much into how Cybertron operated specifically, but I do want to quickly discuss a simple type of machine learning algorithm, and that's something you may have heard of, and that's known as a neural network. So a neural network is able to kind of simulate how neurons in the brain work, because neurons essentially have a certain threshold. If they receive enough of a certain type of neurotransmitter, they are able to then release a signal, which then can carry on. But there are thresholds within the brain. And much like these neurons, there are pieces of a neural network called a perceptron. Now, these perceptrons can be seen as kind of nodes within a neural network. And so for the most simple neural network with only one perceptron, you have the input data, you have the perceptron, and then the output data. So there's only really one layer between the input and the output that does some sort of interpreting. Now, the perceptron in reality is just a bit of math, and it can be complex or it can be simple. Early perceptrons were just kind of step algorithms where if a threshold was met, then it would jump, say, from a 0 to 1. So it was a binary state where if this condition is met, we are going to switch to 1 or true. If it's not met, we're going to keep it as 0, and that's the output. Now, perceptrons advance quite quickly from that because it's not as fine-tuned or fine-tunable. And so they start using what are known as sigmoid functions, which kind of look like step functions, but it was slanted a little. So you have this kind of linear or nonlinear range in which the perceptron can take in data, see what it's like, and then output a corresponding value. And now the nice thing about these sigmoids is that they can be adjusted. So for example, if it were a linear function going from 0 to 1, where if you input, say, a certain signal, it will output a 1, or if you input another different signal, it will output a 0, but also has a continuous range between the two, you can kind of tune the parameters of, say, that linear function to output based on the input data how you want it to.
Well, I think important thing about neural network is it really try to emulate how the brain works, because in our head we have like neurons with like dendrites and axons part of it, but which each one are connected, right? And I think we already know that it fires some kind of electrical signal to the other one. But we don't really know how the information is stored exactly, or I try to not use technical terms, but like how information is processed from one neuron to another, and those sigmoid functions or those functions that try to emulate that, right, and or try to guess of how that would work. Well, not necessary for our brain, but for the learning purposes, how exactly should we filter information or filter signal from one layer of neuron to the other?
Sigmoid function looks like a hyperbolic tan function. Just putting that out there. But anyway, yeah, it's interesting. I think sigmoid functions or hyperbolic tans or any function that looks like that. It's like a switch. It's like a step function. Think of a step function. You have something at 0 and then suddenly it just switches on to 1. But it does it smoothly with the sigmoid function, so it's more realistic. Or instead of like going like boop, it like slowly switches on. So I think they show up a lot when you're dealing with anything, because they show up in my work, but also like I can imagine like a circuit or something where you switch it on suddenly, where a toy model would be you use a step where it instantaneously switches on. But if you use like a sigmoid function, there's like some tiny time where it takes time to switch on. So you can like the neurons fire or something. You could describe it with a sigmoid function, or I don't know.
Well, you can use also linear function, just
That's the
for
property. In the middle of that function, you can approximate to be linear as well.
Yeah, but some people straight up use a linear function with a cutoff. So like let's say if it's below 0.2 is 0, and then above 0.2 is just linear. Y equal x up.
That would work too. But then you have some discontinuities in it, so theoretically it's not as nice. But
yeah, but like you're training the data, right? So discontinuity, I don't think it matters that much.
Computers don't like discontinuities very much, I think. But
this is actually debate that's going on now, is what's the best kind of function to use? Is it just linear? Is there something more complicated? Is it not something that's actually a function, but just something that's a bit more numerical or non-calculable in an easy way? So there's a lot of research and activity going on with how this idea of a perceptron should be handled. But what happens is that these neural networks, they don't just have one of these perceptron with one of these sigmoids. They have a whole list of them that, say, can act like the first layer. So instead of taking your input data and putting it into a perceptron and getting some sort of output from it, instead you might have 100 of these perceptrons in which the data is input to all 100 of them and then output again. Or you might have multiple layers of these perceptrons. So you might have the input data inputting into 100 perceptrons, which then each input into 100 perceptrons in the next layer. And then the next layer might be 100 perceptrons, and then you get an output of some sort. And so you start to deal with these large amounts of sigmoid functions, whatever they may be. And when you're dealing with that, you don't want to have to tune them all by hand. So this is where the machine learning part of a neural network comes in. And it's when you use training data to say, okay, this is the input, this is what the output should be. So it's a very, very simple type of example. We can look at handwriting. So if you were to take, say, a 16 by 16 grid of pixels, and you input these pixels, they are either black or white, and they're in the shape of a 6. So it can be a handwritten 6, but just where there's been writing, there is a black pixel. Where there's no writing, there's a white pixel. So this 16 by 16 grid will give you a total of 256 pixels. And so you can input these in as the single input data, and then that's distributed to each of the different perceptrons within the first layer. And you can change the number of layers that you want depending on the complexity, knowing that the more layers there are, the more time it takes.
I think you mean neurons. Perceptron is an algorithm. Like the whole thing is called perceptron. Like it's called neural network. Each one is neuron. A perceptron is the algorithm for classification.
No, a perceptron is the specific kind of module that takes the input and then feeds an output into it.
Yeah, but each neuron is not. Well, perceptron is a holistic thing, right? Because let's say if the 256 pixels, you need 256 neurons in the first layer, and then you can do whatever you want. Maybe you want to recognize a 1 to 10, and then you need 10 neurons at the end layer. And in the hidden layers, you could have whatever you want, but the perceptron is the algorithm or like the method of classification.
In this case, I learned like perceptron as being kind of analogous to neuron, where you like can have many perceptrons within a row, kind of like how you can have many neurons that take input and then provide output to even more neurons or more perceptrons. But I'll try and avoid that language just to avoid confusion. in case there are different interpretations of it. But in any case, what you can do is you can input this data. For example, this handwritten 6, that's in a 16 by 16 grid. You input it, it's then fed into the first layer of the neural network, which then passes it on to, let's say, second layer. So let's just do a 2-layer neural network, which then passes it on to the output. And you can say, okay, since this was the first one that we put in, we aren't really expecting much from the output. But what we can say is that the final output should be the number 6. So we have this handwritten 6 that's in black and white, and then the output should be 6. So what the algorithm is then able to do, as you're training it, is it's able to work backwards and say, okay, how can we adjust the parameters of each of these individual nodes within both layers of the neural network to make sure that the result should be 6 when something like this is input. And then what you can do is once those have been adjusted and tweaked, you can put in another handwritten number, let's say this time a 5. And so again, it's just a black and white image of a 5. You input that, it says, okay, we don't know what this is. And then you say, okay, this should be a 5. And then it goes back and adjusts those parameters again. So it keeps adjusting those parameters. And when you input many thousands or tens of thousands or even hundreds of thousands of these images of handwritten letters, what you can do is you've adjusted all these specific nodes within the neural network to make sure that whatever is input is able to output the correct value in the end. And so in this case, this is used for handwriting recognition, where you are able to input, say, a phone number. It can cut those into individual numbers, input them into the system, and then output them. So you can get the phone number written as text within a computer. And so this is a very simple example of how our neural network can work, but you can imagine how this can be used. So for example, if you're looking at particle physics data and you're saying, okay, we're going to input these energies and we expect, say, an electron to appear, or we can input these energies that we've measured from a particle detector and say, okay, now we expect a positron or a proton or a neutron or whatever have you. And then we can input new data and say, okay, what's being detected here? And it's able to adjust those parameters in such a way that it can guess. And then you can test the accuracy with testing data or validation data.
Oh yeah, I just look it up to confirm. Perceptron is also like an algorithm, like I said, but it's also like a type of artificial neuron too, I think. So
we're both right. Good. Yeah. But in this case, that's an example of a very simple neural network. And again, they can be a lot more complex. So the more perceptrons or nodes that you have within each layer and the more layers you have, you increase the complexity, but you also have the opportunity to increase the accuracy. Now, of course, there will be diminishing returns, and this has been also well studied of, okay, how many nodes do we need per layer, and how many layers do we need to get the most accurate without breaking the bank in terms of computational efficiency. And so for larger problems, such as, say, if we're looking at astronomical images and trying to figure out, okay, where are neutron stars, for example? And so you're using this image recognition based on telescope data to try and figure out, okay, this looks like a neutron star. Or if you're using spectral data to figure out, say, what species might be in a forest, then you can use these machine learning algorithms. You can train them saying, okay, this is what the spectral signature of an oak tree looks like versus a maple tree versus a pine tree. And then you can say, okay, here's a brand new image you've never seen before. What's going on here? And then you can also test the accuracy. So these machine learning algorithms are able to learn based on very large training data sets. And then you can validate their accuracy based on these validation training sets, which can sometimes be the same data sets that have just been divided. And this is something that's common in research where we have large data sets, we kind of split them, it might be 70% of that data is for training, the other 30% is for validation, and we can actually define these algorithms and how they work, and how well they work.
Well, I feel like, a lot of these training feels like physical training for like sports or martial arts, right? Because like what you do is basically go through routine as like what sport? Let's say um like soccer, right? You kick a ball and you learn how to kick a ball specific ways. But when you actually play, the scenarios or the circumstances that come up, not necessarily as you practice, but your practice actually helps you deal with those new situations that come up. Like that's why like it's so much fun to watch or to play, because even though you practice kicking the ball the same way 100 times, it actually helps you kick the ball when it's in a different place, or you learn how to deal with different things just from limited practice, which, if you want to be super competitive, that's not always true, right? You have to practice with other people and learn more and more about different patterns and scenarios.
Exactly. There's actually a really good book by Joshua Foer called Moonwalking with Einstein, but it talks about memory and how memory works. He goes and interviews a bunch of people and then even takes part in some experiments himself on memory. But one notable example in that book is about chess players, where the top chess players in the world, essentially, they just have really well practiced memories in terms of chess. So some of these chess masters where they're able to, um, win pretty much any game they go into, they can recognize movements from previous tournaments because of the fact that it's in their memory. So they've trained themselves. And even people like Magnuson, it took them a lot of time to learn. And mind you, Magnuson was a child prodigy in chess, but they'd started quite early on and start memorizing these moves and techniques. And that's what it takes for chess is just a lot of memorization, even if it is kind of subconscious.
Do you mean like Magnus Carlsen?
Yes, Magnus
Okay.
Carlsen.
Yeah,
Yeah,
I
not
I
Magnuson.
was reading something on like Hikaru Nakamura, which is the American um, chess guy, right? And he said one of his biggest mistakes was playing Magnus casually. I think a few games, so that Magnus learned his style, and just casually, and apparently it makes him like it just works for him because now they know the tricks. I think that happens a lot in sports, in certain sports, right? Like especially when it's strategy based. If you play this guy a lot, even though he beat everyone else, but you know how he works. And there was like a tennis example too, right? Where he would that guy would lick his lip when he's serving a certain place. I was like, wow. And they never tell the guy until like he retired. And the guy's like, oh, it's like he read my mind.
Yeah, and it's interesting how the brain works and how we're trying to use these algorithms to try and simulate. But the one thing with these machine learning algorithms is if you train one to recognize handwriting, then it's not going to be able to tell the difference between a cat and a dog. And I think that's where a further um, discussion about intelligence and artificial intelligence and a more generalized algorithms for image recognition or for learning is worthwhile. But for now, we're running out of time. Does anyone have any final things to say about this?
Completely unrelated, but talking about this reminded me of a conference I was at on analog gravity. And there was a guy who gave a talk called Language Models for Simulating the Dynamics of Quantum Systems, which I don't remember, but I remember talking about these, like you have the grids, you have the handwritten letters in them, and somehow you can apply these same pattern recognition things to quantum systems. And it kind of makes some sense, but I don't remember the details. I just thought it was cool that this has more applications than you'd think.
Well, the quantum many body systems, the way one other way to solve um, that system is to use the tensor network, or well, the neural network is a form of tensor network, and basically it looked really similar. Create a bunch of networks connected to the specific way, but the activation function is not going to be like sigmoid or something. It's probably some quantum operators, right? So it's actually like the field is very useful in solving what's called high degree of
Mm-hmm.
connection systems. Yeah, it was good. Technically, what I did for my master was a tensor network. Was more it's complicated in a different way. It doesn't have that many what you would call neurons, but the connection between each is quite
Mm.
complicated, right? So it's a different way of visualizing or realizing your system to solve it.
Very cool.
Yes. So before we get to the story today, uh, I just want to mention how you can get into contact with us. There are many different ways which you can reach out to us, whether it's through email or Instagram. We are found on email. We are hyperthesispodcast@gmail.com. You can send us an email with questions, comments, or queries. You can also reach out to us if you're an expert in your field, especially if you're an expert in AI for this episode. We would love to hear your thoughts on it and what your research is about if you're researching it. You can also reach out to us on Instagram. We are at the Hyperthesis, where we post updates when we post episodes, along with other updates. There's some memes there sometimes, but no pressure on Liam. It's a busy time of year, but if he makes a meme, we would love to see it. Yeah, you can also send us a DM on there if you have, again, questions, comments, or queries. We have a YouTube channel. I believe you can reach out there. You can also listen to our episodes on YouTube with some beautiful animation by Pheely. We are pretty well up to date with YouTube. We might be like at times an episode or two behind, but it's pretty good at being updated. And you can check out some bonus content there, including some community posts. So make sure to get yourself subscribed and like our videos. Just put them on in the background and listen to them. If you're listening to us, congratulations, you have found us, and hopefully you can continue to listen to us, especially if you can't go outdoors due to the extreme cold. I know here it's supposed to get -40 at least, or at most tomorrow, so it's going to be quite cold throughout Canada and North America. So give us a listen inside with your loved ones or whoever you're stuck inside with. We are found on Spotify, that's where we're based out of. But you can also find us on Google Podcast, Apple Podcast, Amazon Music, or Audible. Pretty much wherever you find your podcasts, you can find us. So feel free to share us, give us a rating, subscribe, and thank you for listening.
So the story for today is I call it the AI endgames or apocalypses, whatever you want to call it, that could happen. So we talk about artificial intelligence, how it works and such. The examples we use so far is not very complicated, right? Like the AIs these days that you see, for example, those large language models and such are vastly complicated. Like even for image generation, the analysis, it's been used like to, I don't know, like this thing has been discussed ad nauseum, right? But there are scenarios that people dream of in the future, what AI could be, and I'm gonna talk about some of them. So some of you may have heard from movies or have seen some or read some sci-fi, and I think a lot of plots on AI come from these ideas that what it could be. So if you have a really powerful AI, what would happen? So first is the concept of boxed AI. So the concept that this super intelligent, we will confine it to a box, and then we have these human gatekeepers that take charge of it and use it to advance humanity, like find scientific breakthroughs or do some advanced logical reasoning. So, and we will not allow it to take over the world or think outside the box. It's really a tool. So, like a super AI computer that's in a box. But we also saw a bunch of movies where, oh well, the AI is gonna go rogue and breaks out, try to control the world. But that's one of the scenarios that it's like a computer, right? When we first have computers, like, well, is the computer machine is gonna take over the world? And so far, it has been in the metal chunk in in your bag or in your house, right? There's a bunch of metal chunks. So it's really similar scenarios to what we have called computers right now. But in a second scenario, the opposite could be true. That instead of we gatekeep the AI gatekeep us. So basically, this idea that the AI is gonna be smart enough to prevent us or prevent other AIs from making other smart AIs. So basically, it self defines limit to not basically have a divergent AI that goes like super intelligent in the wrong way. So it basically put everything in a box. Like you cannot create a super intelligent AI anymore because it's gonna destroy everything. It's destroy themselves, destroy ourselves, and basically it prevents all other super intelligences. Well, it might have to slow down technological processes and give time for society to advance, for the humanity to advance. Basically, almost like a super intelligent, what's it called, protector AI that gives human like this, you know, we believe that we control, we believe in creating things, live our life. And one could argue this almost akin to concept of deity or some alien overlord. It's the same concept, right? But these are AIs that actually decide what technological advance are allowed and such. And humanity gains some illusion of control and restricted by this AI that doesn't want us to build, or doesn't want all the AIs also to build more intelligent AIs. The basic gatekeeping us in a box. Well, we can put that scenario to a more extreme case where, well, how about AI just think of us as animals, right? Because we are upright ape with crude tools. I quote that from the movie Ex Machina, great movie about AI. And similar to, I think, 2001 Space Odyssey too, right? It's highly advanced aliens see us as animals, like, and they keep us in a zoo, the human zoo. So that could happen with the AI too. Hey, maybe they talk to other AIs. Look at this. This is the organic, crude animal that's supposed to compute and learn things at a very slow rate. So please keep preserve us as endangered species as we do to animals now, right? So because maybe humans would go to war and we have very few left, and the AI is like, well, we got to preserve these because it's for nature. So that is one of the concern ish. So we might be the robot pets. Who knows? So, anyways, let's go into a more optimistic one. So those are scenario that's a little more pessimistic. So if an AI somehow conclude that the human is actually necessary risk. Actually, sorry. Let's not go too positive yet. Let's go for the route of human extinction. So if the AI decide that the human is a waste of resources, we are like plague on the planet, and they should eliminate us, torch the sky, kill all of us, like sounds like the Matrix. But yes, that they should make human go extinct or use it for farm, or not as human being basically. So it could program to devalue human life. But it could happen, if you, let's say, you program it to preserve Earth. And somehow the conclusion that AI comes about is to destroy all humans because humans does a lot of things to Earth, right? The pollution and such. It's not a uncommon train of thought that people could go through. And, it's kind of flawed um, moral wise, but computers, who knows, right? With the AI. So if they deem that human is necessary to destroy human or just keep them as a very endangered species, basically, So if they were programmed with this incomplete or messed up form of human values or what it means to what the value of life, then that could happen that we will have some kind of Terminator scenarios. Well, however, we also can have some kind of utopia that could come from AI. Right? So there is this video game come out in PlayStation 4 a while back called Detroit Become Human. It's about the cyborg or the machines that help us in our daily life that looks like human but they're actually cyborgs, and how your decision in the video game can affect the storyline. Are you gonna become a tyrant? Are you gonna become a revolutionist? Or are you gonna live peacefully, coexist with human? So there are, I think, one of the concepts is to advocate for libertarianism, where everyone, even if it's either be human or cyborg, can live peacefully, have the same rights, and recognize different diverse, not just for species of humans, but for cyborgs, and we live together and prosper together. We help each other. So that could also happen. And the other way of the utopia is the benevolent dictator. So what if we have this super intelligent AI, but actually in our best interest? Well, that's how usually the tyrant starts, right? Like, well, we are here for your best interest. But if it's a machine who actually have some design that is designed or design itself to sustain humanity, right? So that could be also what we call benevolent dictator. But there's a lot of caveats that come with it. It's really easy to imagine that benevolent dictators would turn into the previous dystopian scenarios that we talked about before, where like, well, even though it's for humanity, and then somehow it realized we need to kill some humans or some human life are worth more than the others, is it's still an ongoing ethical debates, right, or moral debate. It's like what does it mean? Does the death penalty as a proper thing to do, right? So they are, well, even though they have an optimistic side to AI and the AI overlord, I still think it's prone to errors, as maybe not as much as human decision in each decision, but holistically it's still prone to catastrophic failures like any auto-designed system. And this idea has been explored extensively through science fictions, movies, or even papers who study AI ethics. And I think it's become a bigger field. How do policymakers make sure that the AIs are being trained not to be violent or for good purposes, which in a way is really hard to control. How do you enforce that if anyone can just download the model and train to whatever they want? So in the future, we have to be really careful about how we manage our AIs and what power are we allowing AIs. So these certain scenarios that do not happen. And that is the story for today.
Well, thank you for that frightening but maybe hopeful story on AI. And thank you for joining us for our discussion on machine learning and AI and talking about some radar as well, which is always fun. So with that, have a good day and thank you for joining us. Bye, everyone.
Take care.
See ya.